Hey everyone, and welcome to this explainer. Today, we're going to completely demystify the real number line. We'll be taking those abstract concepts like rational numbers, irrational numbers, and messy decimals, and literally pinning them down visually. By the time we're done here, you won't just understand these numbers conceptually, you're going to know exactly where they live on a physical line. We're going to build this understanding step by step using the Unit 1 text on real numbers. Let's get into it. Here is our game plan for today. First, the real number line. Then, decimals on the line. Third, rational versus irrational numbers. Fourth, fractions to decimal conversions. And finally, mastering number line plots. All right, let's kick things off with part 1, the real number line. Okay, let's dive into this. The textbook gives us this incredibly straightforward two-step rule for plotting any fraction. Let's call it A over B. Step 1, you just look at your denominator, that's the b, and you slice up the space between the integers on your number line into b equal parts. Step 2, look at your numerator a and simply count out that many parts starting right from 0. You move to the right if it's positive and to the left if it's negative. It is really that simple. Let's actually see this rule in action with a couple of textbook examples. Take plotting 1/2 and -1/2. Since the denominator is 2, you just slice the space between 0 and 1 right down the middle into 2 equal halves. For positive 1/2, you hop one space to the right. Negative 1/2, you hop one space to the left. Boom. Now look at example 2, specifically 1 and 1/5. You just jump straight to the whole number 1. And then, for that leftover fraction, you chop the space between 1 and 2 into 5 equal pieces and hop forward just one of those pieces. Moving right along to section 2, decimals on the line. And this brilliantly illustrates a really cool point. Whether a fraction gives you a clean, terminating decimal, like 5/4, or a super messy recurring decimal like 11/6, the physical way we plot it, it doesn't change at all. Take 11/6, for instance. If you punch that into a calculator, you get this ugly repeating decimal. But on the physical number line, it's an absolute breeze. 11/6 is literally just 1 whole and 5/6. So you find the number 1, divide that next gap into 6 equal parts, and just count 5 parts over. This visual method completely bypasses all that messy decimal arithmetic. Next up, section 3, rational versus irrational numbers. So the absolutely crucial point here is nailing down this exact distinction. A rational number, when you write it out as a decimal, is going to do one of two things. It will either terminate, meaning it comes to a nice clean stop, or it'll be non-terminating but recurring. That just means it loops a specific pattern forever, like 0.3333. An irrational number, on the other hand, is your wild card. It is non-terminating and non-recurring. It just goes on forever and ever without any repeating pattern whatsoever. Knowing this golden rule is literally your cheat code for the rest of the worksheet. All right, armed with that golden rule, it's time for workshop mode. We are looking directly at exercise 1.1, question 1, which asks us to identify and sort a pretty long list of numbers into rational and irrational columns. And classifying these is super fast now. The rational column gets all those clean fractions of integers, 1/5, 2/8, 22/3, and 11/12. If you divide them, they're either going to stop or repeat neatly. But that irrational bucket, that catches the square roots of non-perfect squares. Stuff like the square root of 2 over 8, 5 over root 6, 1 over root 3, root 8, and root 5. And hey, it doesn't even matter if they're divided by a whole number, they remain irrational. We also see famous constants like e, pi, and 1 over pi hanging out here, which naturally belong in the irrational group for sure. Speaking of pi, question 5 from the exercise actually asks us this directly. Give reason why pi is an irrational number. I want you to take a quick second here. Predict the answer based on that golden rule we just covered. Well, if you remembered our definition from earlier, you absolutely nailed it. Pi is irrational specifically because its decimal representation is non-terminating and non-recurring. It goes on infinitely, 3.14159, and so on, without ever settling into any repeating mathematical pattern. So it simply cannot be perfectly expressed as a fraction of two integers. Okay, let's move into section 4, fractions to decimal conversions. Let's see how this builds in question 2. To solve this, we actually need to do the long division to test the decimal types. If you divide the numerator by the denominator, like 5 divided by 8 or 49 divided by 8, the division eventually leaves absolutely no remainder. They terminate perfectly cleanly. Even 207 divided by 15 stops cleanly at 13.8. But if you try dividing 4 by 18 or 1 by 15, you're going to find yourself stuck in an infinite loop. The remainder literally never reaches zero. Instead, they just spit out a repeating string of numbers that never ends, and that proves they are non-terminating recurring decimals. And finally, Section 5, Mastering Number Line Plots. So let's bring it all together. Question 3 gives us a list of rational numbers and asks us to actually get them onto the number line. Now notice how this asks us to apply the very first basic two-step rule we covered at the very beginning of this explainer. Here is the strategy to breeze right through this. Remember, your denominator is the boss. For 8/10 and -8/10, the denominator is 10, right? So you just divide the space between 0 and 1 into 10 tiny slices and count out 8. Simple. For 1 1/4, your boss is the number 4, so you make 4 equal parts between the integers. For 2/3, you slice the gap into 3 equal parts. Seriously, just listen to the denominator, make your slices, and start counting. Moving on to question 4, we actually run into a bit of a trick question. It asks, can you make a list of all rational numbers between 1 and 2? I want you to really think about this visually for a second. If you look at the space between 1 and 2 on our line, can you honestly list every single fraction that fits inside there? The answer is a resounding no. There's no way. It is mathematically impossible. The real number line is infinitely dense. I mean, think about it. Between 1 and 2, you've got 1.5. Between 1 and 1.5, there's 1.25. And between those, there are infinitely smaller and smaller fractions. You could literally spend the rest of eternity trying to list them out, and you would never, ever finish. Now, what's really interesting about these true or false statements for question 6 is how fast we can validate them just by leaning on our foundation. Is 5/7 irrational? False. It's just a simple fraction of integers, so it's rational. Is pi irrational? True. We proved that one earlier. Is 0.31591 with no repeating bar, non-terminating and non-repeating? True. There is no pattern indicated there at all. Is the decimal 0.123 with a bar over it recurring? True. That is exactly what the little bar means. Do 1/3 and 2/3 lie between 0 and 1? True, because the numerator is smaller than the denominator. And lastly, is 1 over the square root of 3 rational? False. That square root of a non-perfect square completely poisons the fraction, turning it irrational. Listen, if you take only one thing away from this entire explainer today, let it be this ultimate cheat code for real numbers. If it terminates or repeats, it's rational. If it goes on forever without a pattern, it's irrational. That simple logic absolutely guarantees you'll be able to classify these numbers. And that wraps up exercise 1.1. So look at the numbers around you today on price tags, speed limits, cooking recipes, whatever. Now that you've mastered the rules, can you confidently picture exactly where they belong on the infinite real number line? Keep that mathematical curiosity alive. And hey, thanks so much for joining me on this explainer.